Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Okay, so this is a fun conceptual problem here. So I have a couple things written already. So I have the magnetic field. We're given in two directions. One of the directions is in the negative y component. The other one is in the positive x component. And then we have in blue, we have the velocity of the particle traveling in the positive z component. So this is what it would look like in 3 dimensions. 3 dimensions can be something that can be sometimes a little bit difficult to conceptualize, but imagine this x-axis as coming out of the page, and then z and y are the planes of the page. So you can imagine the negative x direction would go into the page this way, and then z would just continue down, or negative z. So this is in 3-dimensional space. We want to find the magnetic force at a location here. It can be anywhere along this blue line here. We're just going to make it right here for simplicity. It doesn't so much matter the distance for what we're trying to calculate. So we want the force here. So you have two components of force now that are affecting that location. One here from this component of the magnetic field, and one here. So this is coming up towards it, and this is coming to the right diagonally. So we'll need to do two separate equations. So we'll do the math over here. So to get force, we use the equation F is equal to the magnetic field times the charge times the velocity. Now, this typically has a sign of the angle between the force and the velocity, but as we can see, all three directions here, both red arrows and the blue arrow, are all perpendicular to each other, where this is a right angle and this is a right angle. So it'll be sine of 90 degrees or sine of pi over 2 in radians, which is just 1. So we don't need to keep that into consideration here. So this is the first one. We'll say this is from the one in the positive. We'll call positive x direction F1. And the negative y direction F2. F2 is negative y, F1 is positive x. So for the positive x direction, plugging in, we have the values for B, Q, and V. Plugging all of those in, we find that this force is equal to 0.004. And it's important to note, everything we're given is to two significant figures, so we'll want to keep the 0. Everything is in SI units, so we'll be in newtons here. You can also write this in scientific notation as 4. We want to keep the 0. That 0 is accurate, so it needs to stay there. This is times 10 to the minus third. And that's the force from the positive x direction component of the magnetic field in newtons. So we'll need to do it again for the second part of the magnetic field, F2. Same equation, same thing, just different numbers. You plug in those numbers and you'll get 5.5 times 10 to the minus 3. Exact same process as the first one, but these are in two different directions. So now what we'll want to do is go and look and see what direction this force will be in. That means we get to use the handy-dandy right-hand rule. So let's go back and look at F1 to start. So we have a force. Using the right-hand rule, you want the force to be your middle finger or your palm, depending on which version of the right-hand rule you're using. So typically, I like to start and point my pointer finger in the direction of the magnetic field, which would be the red arrow here. So that's your pointer finger. Your thumb, you want to go in the direction of the velocity, which is the blue arrow. So right now your hand should kind of look like a gun symbol. You have your pointer finger pointed out in the negative x direction and your thumb pointing up in the z direction. Now if you point your middle finger the direction your palm is facing, so all three fingers are perpendicular to each other, it's going to point straight out this way, which means that for F1, our force is in the positive x direction. Or if you have experience with vectors, this would be in the positive I hat direction, the unit vector I. But we can just say it's in the positive x direction here if you don't have any vector experience. Oh, I'm sorry, that's for F1, not F2. So F1 is in the positive x direction, or I hat. Because this is three-dimensional space, you really need to keep track of your directions. They're very important, especially for equations like this, where you have three different variables that are all pointing perpendicular to each other. So that's F1. So I'm going to draw the force in green. That's at this point here. So that's pointing out this way. Same direction as the x-axis. Right at this point, or any point along this blue line, it'll be pointing in the same direction. Now let's go look at F2. Oh, I'm sorry, that was for F2. I did F2 on accident, so we'll write that as F2. F2 is in the positive x direction. This is why labeling things can be really important and help you from getting a little confused. So that was for F2. The pointer finger should be along the magnetic field, which is what I did for F2. Now for F1, it's pointing out. So you want your pointer finger to be pointing straight towards yourself, and your thumb along the blue arrow here for F1. So we have pointer finger in this direction, thumb pointing up in the z direction, and once again, the direction your palm is facing, point your middle finger that way, and that'll point this way. So your three fingers in this case, this should be your thumb, this would be your pointer finger, and then your middle finger will point this way. You kind of have to twist your right hand around to get it to do that, but it's important that you use your right hand because your left hand will give you the reverse, or if you had of what you would get if you had a negative charge. So these are your three fingers. So in this case, for this is F1 now. F1 is pointing in the positive y direction. So F1 is positive y. Okay, so we have two force components at this location. We want to find the magnitude of the total force on this point. So the magnitude, there's a formula for finding the magnitude. You can also make a triangle and use the Pythagorean identity or the Pythagorean theorem. We'll do it over here. We have two triangles, or we have one triangle, two lines. This was, double check, that was, let's label them up here again. So this one was, the positive x direction was from F2. So this was F2. The positive y direction was from F1, just to keep them straight. So we have F2 here, and then this is a right angle for F1. So now this makes a right triangle if you connect here to here. And we have each side here. So to find what this value is here, use Pythagorean theorem, which is this quantity that we found. I'll write it out for you. So you have, we'll call this C, this is B, and this is A. Pythagorean theorem says that C squared is equal to b squared plus a squared, or a squared plus b squared. It doesn't matter what order you put them in. So we want to find c in this case. So to find c, just take the square root of that. We want b squared plus a squared. So it's the square root of our answers we found for the forces squared. This is also the distance formula. This is where the distance formula comes from. It's the distance between 2 points. So you can use the same thing as well. So this will be your b, and this will be your a. Plug those into this equation, and you'll get these are all in newtons. You'll get 6.8 times 10 to the minus third. This is in newtons. Okay, that is the magnitude of the force from both of these components here. And now, looking back at our diagram we have, that will be, so it's from this force and this force. Both of those will push it kind of in this direction. The stronger of the two, F2, will kind of take over it, so it'll lean slightly more this way. But we can find out exactly what that angle is by going back to our triangle we have here. So we have, in geometrical terms, we have each of the two legs. And so A and B are the two legs, C is the hypotenuse. So if we want to find, so what we're looking for is the angle of the force to the velocity. So we want this angle. Now to find that, you just take the inverse tangent of A and B, or in this case, F1 to F2. So what we want to do here, let's make some space. We want to take the inverse tangent, which gives you an angle, of F1 to F2. The force from F1 to the force from F2. And this is something you can just plug right into your calculator. And this gives you an angle, theta, in degrees. You should get 36 degrees from that, from your two numbers for both forces. And there you have it. Your two numbers you have here, the magnitude of the force, 6.8 times 10 to the third, and your angle is at 36 degrees. There you have it.